Hello everyone. So this time we're going to be going through some deformations and axial loaded bars. This is that case I was talking about where we're going to have a system of bars. But first we got to start off with the easy part. Like I said earlier, in many cases we do not want the percent elongation. We'd rather just know the deformation load causes. And we can do this using Hooke's law and our definition of stress. So we have this right here, and then it turns into our Flee equation, which chapter 4 goes into in quite a lot of detail. But we'll reiterate it here. This is coming from just knowing what stress is, and this, as you might guess, only works in our elastic region. Once we get outside of this, this breaks down, no longer works. Now let's talk about some sign conventions. Look at this. Same elongation, but the forces are pointing in two different directions. So for this equation, tensile force is considered positive. Okay? It'll lead to a positive elongation. The bar will become longer. Compressive loads, where the force is pressing down into the part, those will make it be considered negative. Now, if you're really unsure about the force conversion, just think shorter, negative, longer, positive. Shorter, negative, longer, positive. Anybody get it from there? Figure out what sign the force has to have in order for that to work. Okay. Now what about a system of bars? You can see there's 3 bars here, each of them with their own cross section, and there's also some point loads being applied to them. So how are we going to solve this? This looks kind of like a nightmare. But it's not too terribly bad. Our elongation will simply be the sum of the elongation in each of the individual bars. So I calculate the elongation for this bar, and for this bar, and for this bar, and then I add them up, and I get my total elongation, or the elongation to a particular point. It's not going to be too bad. In cases where we have a cross-section that is just increasing, not in nice little gradients, but as a function, well, then we'll have to do an integral. Our sum turns into an integral, where modulasticity is still constant, hopefully, for this. We'll integrate from 0 to wherever we care about, and then we'll integrate the force over the area. The force over the area. So in these cases, the integrals aren't usually terrible. We won't do too many of these kind of problems. It's much more often for us to have the system of interconnected bars, like the previous example. Okay, so let's try an example before I let you go. So what do we have? Well, we have a compound axial member, which is shown, and consists of a 20 millimeter diameter solid aluminum segment. That's right there. Oh, sorry. A 24 millimeter diameter solid aluminum segment right here, and right there. There you go. And a 16 millimeter diameter solid steel segment right here. What do we want to know? Well, we want to know the displacements of points B, C, and D. How we're going to do this? We're going to use that equation we just learned, which is delta is equal to the sum of the force times length, just the flee, sum of the flee. What is force? We're going to have to figure that out as we go along. So let's try it out. So what we need to do is we're going to cut the bar at various points. We're also going to make sure that it's as far away from these point loads as we can. So cut the bar through 1, and then everything else ceases to exist. It's grayed out because it no longer exists. Just don't worry about it. It's not there anymore. Once we've done that, well, what is force 1? Well, you can see there's only one force pointing in the opposite direction. So force 1 has to be what? What does that have to be? It has to be 4 kilonewtons. So I take my sum of forces in the x direction, and I get 4 kilonewtons. Boom, not too hard. Okay, let's try a second one. Cut at force 2. As a note, this is not one set of 10 kilonewtons, it's 2. So that's 20 kilonewtons there. It's the only way we can maintain an equilibrium. We have 28 kilonewtons pointing one direction and 28 kilonewtons pointing the other direction. So now we have force 2, and it's pointing in the positive x direction, and we have 3 other forces we have to take into account. So let's add them all together. Sum of the forces in the x direction. Well, it's going to be force 2 minus 4 kilonewtons, it's pointing in the opposite direction, plus 20 kilonewtons, which gives us negative 16 kilonewtons. Force 2 will be negative 16 kilonewtons. Which means we honestly have force 2 pointing the wrong direction. That's okay. We'll just leave it as is right now because it would be compressive. We always draw our lines in tension because for our Flee equation, compression is negative. So we'll leave it as a negative number. And then we're going to cut it again. And we're just going to keep this right side because why keep this long side with all these forces when I only have to solve for force 3? I don't care about all those forces. I'll do whatever I can to solve for force 3. And this half has to be in equilibrium as well. So this is pretty easy to see that force 3 will be 8 kilonewtons. It's positive because it's in tension. So yes, the different members don't have to be in the same state. They don't all have to be in compression or all in tension. They can be different. Now, with this in mind, you'll be wondering, well, what about those two forces? Why do we ignore them? Because we didn't need them. Like if we wanted to, we could have gone reverse. I could have cut 2 right here and gotten rid of this side and used them. But you won't need necessarily every single force. They're there, they have to be there to maintain equilibrium, but otherwise we're good. So if we look at this, we can now look at our point loads. Okay, so we have this 4 kilonewton force which is going through there. Remember, it would be a point load, but it gets distributed once it goes through number 1. Then we drop down to negative 16, and then we jump up to 8. If you look at the difference in these heights, well, this is a difference in height of 24. Add that together, that's 24. This is a difference in height of 20. Add those together, what do you get? You get 20. Oops, sorry, wrong button. So now we're going to use our elongation equation for this system of bars. So we get delta 1 is force length over elasticity times area, and it comes out to be 0.364 millimeters. It's positive because it was in tension. For our second section, it's negative because it was in compression. And for our third section, it's positive because it was in tension. And for our total elongation, we add them all up. Or for the individual points, we can figure it out by adding up the any ones we need. So for point B, which is our first elongation, 0.364 millimeters. Point C, sum of our first 2 elongations is negative 0.899 millimeters. And for point D, it moves the sum of all 3, which will be negative 0.302 millimeters. Because that one section of the mill really got compressed. And that's it. That is our problem. So I hope this helped you see how you use this elongation equation. And I appreciate you listening. I'll see you all next time. Bye-bye.